Okay, welcome back to Logarithms and Exponentials. And in this video, we're going to use logarithms themselves to solve exponentials rather than just using exponential equality. Exponential equality is a fine technique when the equations are simple. But in this case, we're going to start running into things where exponential equality does not work for us. So I want to look at 3 steps here. We're going to use these 3 steps going forward. First, you combine like terms and you isolate the exponentials. And then here's the important one. Instead of just dropping the base on each side because they're equal, we're going to drop the base by applying a logarithm to both sides. And then you simplify it and solve for x. So let's take an example here, and I'm intentionally picking an example that we could do with exponential equality if we wanted, right? Here's how exponential equality would work. You would just say, it's equal base on each side. See those 5? So you would just drop the base and say x minus 1 equals 2x plus 3. And then let's say subtract 4 from each side. So we get subtract 3 from each side. X minus 4 equals 2x. Then subtract x from each side and we get negative 4 equals x. Well, isn't that nice? It's all solved. And actually, this is a perfectly fine way to solve it. It was very quick. But I want to use this problem to demonstrate how you use logarithms. So I'm going to take the logarithm of each side. And for the base of the logarithm, you might be wondering, well, are we talking about log base 10 or log base e, otherwise known as natural log? Are we talking about just some random thing like the log base 17 of each side? There's a very particular log I want to use that will solve this equation. And the reason I want to use it is because it's spelled out for me right here. The base is 5. So if the base of these equations is 5, I'm just going to use logarithm base 5. So let's go. Logarithm base 5 of 5 to the x minus 1 equals logarithm base 5 of 5 to the 2x plus 3. Okay. And now as we think of how we're going to simplify this thing, right, it might look worse, not better. We have to use the power rule of logarithms. If you remember what the power rule is, this says that the log of x to the nth power, okay, so x to the nth is the argument of this logarithm, log of x to the nth equals n times logarithm of x, right? You take that exponent and you move it in front as a coefficient right here. Okay, so what does that mean for our equation on the left here? Well, our exponent is x minus 1, so I'm going to take that and put it out here as a coefficient. I have x minus 1 times the logarithm base 5 of 5, and that's equal to 2x plus 3 times the logarithm base 5 of 5. And at this point, there's 2 ways you can do this. You could imagine dividing each side by log base 5 of 5. And look, that's going to cancel out. And likewise, it's going to cancel out both sides, actually, log base 5 of 5. You can do it that way. Or you can also recognize that log base 5 of 5 is just 1. You don't need to divide by anything. Remember, log base b of b, regardless of what b is, will always equal 1. So those cancel out. Those are each 1. Anything times 1 is just itself. So this becomes x minus 1 equals 2x plus 3. And now we are basically ready to solve this equation for x. So you may be thinking, why would I do this more complicated technique involving logarithms on both sides? Well, it's not a great idea when you have equal bases like we do here. But when you don't have equal bases, it actually comes in very handy. And we were actually doing logarithms the whole time when we did equal exponential or exponential equality, right? And we would drop the base. We were using logarithms without actually writing it down. We didn't show all these steps in here. Okay, we were just using this hidden power of logarithms within us. We didn't write it down, but that's what we were doing. So now I want to start using logarithms to solve these equations. And we're going to start with this one. It's not too bad. 3e to the 11x equals 9. Well, I'm going to take the logarithm of both sides. And just to make things easy on myself, I'm going to choose a logarithm with the same base as the exponential equation. That's log base e, otherwise known as the natural log. So let's do ln of 3e to the, what's wrong with this? Look at this. I've got a 3 in front. That's going to make things complicated for me. Why don't I divide first? Actually, I think this was step 1, right? Combine like terms. So this becomes e to the 11x equals 3. Now I'm going to take the logarithm of both sides. ln of e to the 11x equals ln of 3. Well, ln of e to the 11x is 11x times ln of e, natural log of e, and that's still equal to log of 3, natural log of 3. And if you remember, ln of e, right, what is that? That's log base e of e, right? And anything where you have an equal base and argument crosses out to be 1. So this left side is just 11x, right? This term right here is just 1. And then on the right, you still have ln of 3. So our final answer becomes x equals 1 over 11 times the natural log of 3. Okay, that's what we get. And you couldn't have done that with exponential equality because you didn't have equal exponents. Now, this one's a little more complicated. In appearances, it's really not if you take a moment to look at it and think about combining like terms first. Look at what we've got. We've got a 7 over here, a 14 over here. I can do something with that. Let's rewrite it as 9 times 5 to the 10x minus 7 from each side. So we get equals negative 6, 5 to the 10x, and we're going to bring that minus 7 over here. Okay, so we have, here I'll just write it so you can see. Subtracting 7 from each side, we get plus 7 on the right. And now let's add this thing. That's another like term. You can think of this, let me circle what I mean in particular. Let's use a different color. This right here is the like term. This 5 to the 10x. See, it's on both sides. And you can treat that just like some ugly variable, like one of those Greek letters. So I'm going to add 6 of these things to each side. Add 6, 5 to the 10x, and over here I'm going to add 6 times 5 to the 10x. And how many 5 to the 10x's do I have on the right now? I have 15 5 to the 10x. And on the right, I still have 7. One more step in combining like terms gets us to this. 5 to the 10x equals 7 over 15. And now I am ready to take the logarithm of both sides. So we apply a log base 5 because I'm using a 5 in my exponential. Log base 5 of 5 to the 10x equals log base 5 of 7 over 15. Okay, and now again the power rule right here. Power rule says I can take those exponents and turn them into coefficients. So this becomes 10x times the logarithm base 5 of 5 equals logarithm base 5 of 7 over 15. Okay, which means since log base 5 of 5 is just equal to 1, this is 10x equals log base 5 of 7 over 15. And that means x equals 1 over 10 times the logarithm base 5 of 7/15. And that is your solution to this equation.